Okay, so we'll start the recitation now. Um, okay, so this week's homework isn't so bad too, and for that reason I've decided to like not cover the really easy problems. Basically, in response to some feedback I got from a few of you that sometimes the problems are very easy and you know how to do them, so it's kind of a waste of time for me to go over them again. But I will cover most of what is on the homework, and I'll also do 2 or 3 problems that are a little harder, but that I think are good problems to do. And you might even have to do them in the next homework assignment. I don't know, but I think it's worthwhile to go over them. So I guess before I start, are there any suggestions or questions? I really would like to model the recitation the way you would want it to see happen. Okay, so I guess I'll just stick to my plan, and please feel free to interrupt me or ask me things that might be on your mind that might not be directly related to what I'm doing. So, first, we'll start with exercise 3. Okay, so in this problem, this is based on exercise 2, and we're given the following data. So suppose that it has rained for the past 3 days. So if it has rained for the past 3 days, then it will rain today with some probability. If it did not rain any of the 3 days, then it will rain today with some probability. And in any other case, the weather will, with probability 0.6, be the same as the weather yesterday. And we want to determine the probability transition matrix. Well, this problem, you can't really model it. You can't really model it as a Markov chain if you consider simply the weather of the current day, right? Because whether or not it's going to rain tomorrow does not only depend on what happens today. It also depends on what happened yesterday and the day before then. So the only kind of trick in doing this problem is to adjust your state space to accommodate this extra information that is needed. So now, okay. So the state space would be yes. Let's say it would be the it would be the vector of weather over the past 3 days. So if D means did not rain, yes, yeah, and R means that it rained, then we would have the following 8 possibilities, right? Could either have that it did not rain any of the days. Could have that it rained, well, I guess I'm going to stick to the order that Professor Witt has it here. Okay. Oh, and for those of you who just came in now, just a quick note about the recitation. I will be generally skipping the easier problems because that was the feedback that I got from the previous two recitations, and instead towards the end I will do 2 or 3 problems that are not in your problem set, but that I think are pretty good problems, good things to know, think about, yeah. So that's it, and definitely, feel free to suggest any ways that you might want the recitation to change, or I'm here to accommodate you guys, so feel free. Okay, so now this is basically the whole trick of the problem, because now it is we have 8 states, and it's pretty easy to determine the transition probabilities, right? So let's start by calling the state 0, 1, 2, 3, 4, 5, 6, 7, just for simplicity's sake. And now we're basically given everything in the problem that we need. Because, for example, if it has rained for the past 3 days, then it will rain today with probability 0.8. So what does that mean? Well, it means that P77, 7. So if it has rained the past 3 days, it's going to rain tomorrow, and therefore it will again have rained for the next 3 days with probability 0.8. And similarly, we can definitely say that P76, because that's the only other possibility, right? For each state, the transitions can only have 2 possibilities, because only one thing will change here, right? It could either rain or not rain. So P76 will, of course, be 0.2. And let's do maybe 2 other ones. If it did not rain for the past 3 days, then it will rain today with probability 0.2. So if it did not rain, so if we start from state 0, then it will rain today. So we'll go from state 0 to state 1 with probability 0.2. And similarly, it will not rain. If it does not rain for the past 3 days, well, it will not rain today, and therefore we will transition again into state 0 with probability 0.8. And in any other case, the weather will remain, in any other case, the weather will, with probability 0.6, be the same as the weather yesterday. So let's just take a random entry here. So let's say that we're starting from state 5, then it will remain the same as it is today with probability 0.6. So it will rain again today, and we'll have scenario DRR, so 3. Wait, what? Yeah. So starting from 5, we'll go to 3 with probability 0.6. And then what is the other possibility? Well, we can go either to 3, or it cannot rain, in which case we have DRD, so 2. So I don't know if I've numbered the states in the same way. So from 5, if it rains today, we go to DRR, which is 3. If it does not, we go to DRD. D. Yeah, no, that looks right. So that's kind of the main idea of this problem. And of course, you can fill out all the entries in the matrix in this way. Are there any questions? Let me just make sure that I got it right. RDR. So from RDR we go to DRR or DRD. Yeah. Okay. So that's pretty easy. So let's move on now. So we'll do problem 4. So first of all, before we do problem 4, let's remind ourselves of the definition of a Markov chain. Actually, XN is a Markov chain if we have let's say so if this conditional probability, if the conditional probability of being in state J at time n plus 1, given all the prior history, is simply equal to the conditional probability of making that transition given only the information that we have in the present. And this would apply for all states I, j, and so on and so forth, I, n minus 1, blah, 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 and also for all n. And this is important. One of the major sort of aspects of a Markov chain is the fact that these conditional probabilities remain constant over time. In other words, the probability of transitioning into something into some state from some other state is pretty much a stationary thing. It doesn't change. It's the same probability. So now, given this definition, we're asked to determine if if the following is a Markov chain. Okay, so make sure I got it. All the history. And xn takes the values actually 0, 1, and 2. Now, do you guys think that this is a Markov chain? Given this definition here? Well, probably not, right? Because the probability of making a transition from state I to state J should be constant for all n. Instead here, well, it's very explicitly, it's not a constant, right? It depends on the parity of n. So it's definitely not a Markov chain. So let's say now note that the other property is fulfilled. Like the conditional probability of making a transition from I to J is equal to the conditional probability of making that transition given any prior history. What is not fulfilled is this requirement here, that these probabilities be stationary or be not change over time. Okay. So now let's do problem 7. And just as a motivation of problem 7, I will just briefly discuss the Chapman-Kolmogorov inequalities, and also do that little derivation that's in the book. Okay. Okay. And this is literally the probability of going from I to J in exactly n plus m steps. So let's see. So a neat trick to do whenever we have something like this is to condition, right? So now we can just condition. Actually, let's write this a little nicer first. So let's condition now on the value of the Markov chain at time n. So, but before we do that, I guess we can just write the law of total probability here. This is the probability. Here we just sum up over all the different possibilities that the value of our chain can take at time n. So this is just the law of total probability. And now we can rewrite this in terms of conditional probabilities. And this is a pretty interesting property. So say that you have this conditional probability here, then this is simply equal to probability of A given B and C times the probability of B given C. And you can pretty easily see this, since the left-hand side is just equal to the ratio of the joint probability divided by probability of the event that we're conditioning on. And here it turns out that this is the same thing. Because we get these cancellations. So this is a pretty useful property in this case, and you'll see why. Okay. So now if we consider this event A, this event B, and this event C, then we can rewrite this probability as the probability that xn plus m is equal to j, given both of these events. And then times the probability of xn equals to k, given x0 equals to I. Now let's continue here. Now, by the Markov property, we know that it doesn't we really do not care about what has happened. If we have recent information about an event, we don't care about what happened in the past, right? So this information here has no significance. So by the Markov property, okay. And finally, what is this probability here? Well, does it matter that we start the chain at time n? It doesn't matter at all, right? All that we really care about, again, due to the Markov property, is just how many transitions do we make from the beginning. Doesn't have to. The beginning can be anywhere. So this is just the sum of p k j to the m, or rather m. And of course, this doesn't mean raised to the mth power. I hope you know that. Times p I k to the nth. And this is how we get that derivation. I just thought it was useful to look at it, and especially if you were puzzled by how to go from here to here. Are there any questions? Okay. So of course that definition then So if we were to now consider the probability transition matrix of going from any state to another state in n plus m steps, then this would just be the matrix product of the two individual matrices. So for example, if we have P and we want to know now what is the probability of going from a certain state to another state in 2 steps, all that we need to do is to just multiply the matrices. So it makes our life very easy. It makes it very, very mechanical. So that's just something to keep in mind. So now, okay, so we can do problem 7. Actually, is everyone pretty comfortable with problem 7? It's pretty easy. I don't know if it's yes, no. Well, when in doubt, I'll do it. Okay. So problem 7. So it relies on this example where we have so the weather over the past 2 days is a Markov chain. And say we have state 0 be that it has rained both days, 1 that it did not rain yesterday, but that it's raining today. Then rained yesterday, not today. And state 3 is that it did not rain both times. And we also have this probability transition matrix. Okay. So now the problem asks us to find the probability. So suppose that it rained neither yesterday nor the day before yesterday. What is the probability that it will rain tomorrow? Okay. So this means that we're in state 3. And we want the probability of going from state, so oh yeah, nor the day before yesterday. So okay. So it did not rain yesterday or the day before yesterday. We don't know what it's going to do today, but we're interested on whether or not it's going to rain tomorrow. So 2 days. Our last information is 2 days old. So we want so we're starting from state 3, and we want to go to state 1 in 2 steps. So we don't know what this is. Well, we can just very simply apply the Chapman-Kolmogorov equation now, right? Start in state 3. We must end in one of states. Oh no, 0, yeah. We want this. Yeah, because it could rain today and tomorrow. So, yeah. So, what is P312? Well, according to the Chapman equation, and it's also pretty easy to see, it would just be P31 times P10, oops, P33 times P30 plus P33 times P31. And then P302 is just P31 times P10 plus P31 times P11. Times P31. Yeah, that's right. So, and these probabilities are, these turn out to sum up to 0.26. And in this case, it's very easy to apply this Chapman formula because we have so few states that, well, we can directly see what these probabilities are. Now, another way to have done this would be to just multiply this matrix by itself in your calculator and then read off the P31 entry and the P30 entry and just add them up. So if you don't feel like going through this whole thing, if there are a lot of states, it definitely does become tedious and you might make mistakes too. So, okay. So let's move on. Okay, so from So from problem 14, I'll just do we'll just do one of these matrices. Let's do the most interesting one. Let's do number 4. So here we have 5 states. 1, 4, 3, 4. Okay. So first of all, we need to. Oh, did I just do P3? I did a mix of P3 and P4. Okay. Let's do P3 instead. I like P3 more. Sorry about that. Okay. So when doing these problems, the first thing we need to note is to just identify the different classes of states, right? And by a class, we mean a group of states that communicates, where all the states communicate with one another, which means that there is positive probability of going from one state to any other state in that group. And the reason why it's good to look at classes is because recurrence and transience are class properties. So, in other words, if one state in a certain class is recurrent or transient, then all the others are going to be as well. So, so let's identify the classes first. So, of course, it could be that a certain chain has only one class, which means that the chain is irreducible, and that you can go from any state to any other state. A good example of that is just the random walk, right? You do a random walk on the integers, and there is positive probability of you going from anywhere to anywhere else. So anyway, so let's try and identify the classes. So let's say first. Okay, so this is state 0, 1, 2, 3, and 4. So state 0 and 1, from state 0 you can go to state 1, and then from state 1 you can go to state 0. So those two are definitely in the same class. So let's see. So we have 0 and 1. Now from state 0 you can go to state 2, and from state 2 you can go to state 0, but from state 2 you cannot go to state 1. So state 2 is in a different class. And then states 3 and 4 are in the same class very trivially. And also we see that they do not belong in any of the other classes, because if you go to state 3 or 4, you're stuck there. You can only just continue within those states. So now state 0, 1 is recurrent, because if you go in state 0 and 1, you'll just keep being there. State 2 is transient, because of the very simple fact that these two other classes are recurrent. So in other words, if you go into state 0 and 1 or state 3 and 4, then you never go out of them, right? So and therefore you never visit state 2. So that's why there's positive probability that you visit state, or that with probability 1 you'll visit state 2 a finite amount of times. So, yeah.
More than one state that's transient?
Yeah, of course. I mean, if there were, yeah, you can definitely come up with a ton of examples where a whole group of states is transient.
So they can communicate back and forth between each other, but also
Yeah, exactly. Yeah, because they could end up in one of these recurrent classes and never go out of them and be absorbed, I guess. I think you probably did the Markov mouse thing, right? So that's a classic example. Yeah.
If we start with state 1, we can go to state 2, right? So I think that 0, 1 is not really recurrent.
Go from state 1.
From 1 to 2, you can, right?
Yeah. But you can't go from 2 to 1.
Why?
So they don't communicate. Yeah.
Why can't you go from 2 to 1?
Because when you're in 2, probability of going to 1 is 0.
So it's
I think it's from 0 to 2 because you can't go from 0 to 1 because I think you have it wrong.
yeah.
Intrinsic
Like classes.
Even the classes.
0 to
State.
Oh yeah.
It's from 0 to 2.
0 to 1.
Yeah. Sorry. Thanks. Yeah, of course. Yeah. Any other questions? Okay, so now move on to a different problem. So let's do problem 18. So coin 1 is heads with probability 0.6, and coin 2 probability 0.5. So a coin is continually flipped until it comes up tails, at which time that coin is put aside and we start flipping the other coin. So what proportion of flips use coin 1? So let's define the Markov chain where xn is equal to 1 if coin 1 is flipped on nth toss, and it is 2 if the second one is. Okay. So, and now we can, I think, pretty easily find out what this probability transition matrix is. Because, okay, what is P11? Well, if we're flipping coin 1, we want to keep, what is the probability that in the next toss we're again flipping coin 1? Well, it is the probability of getting heads in coin 1, right? So just 0.6, and it would be probability of flipping coin 2 would be the probability of getting tails, which is 0.4. And of course here, you have 0.5 and 0.5. Okay. And now we're looking for some kind of limiting probability result, right? So I guess it is useful to just remind ourselves of the following theorem. It's a very important theorem. Okay, so for an, I'm going to write it on the board. For an irreducible aperiodic positive recurrent Markov chain, this limit exists, is independent, as you can, or is independent of n, of I, is independent of the starting point. Of I, and if we call pi j this limit, then the pi j's are the unique non-negative solution of, this is very wordy, but it's important. And it's a unique solution. Then the pi j's are the unique solution to this set of equations. And now a simpler way to write this in matrix vector notation, it's one which I always use, would be to just say that pi transpose, pi now is the vector of the limiting probabilities, and we're considering a column vector, so let's say pi transpose as being the row vector, would just be equal to pi transpose times the matrix P. And then, of course, P transpose times E, where E is the vector of all ones, is equal to 1. And this is just a slightly more economical notation. You definitely don't have to use this at all. But I always find it a little simpler. Okay, so now, with this theorem in mind, we're looking for some kind of limiting probability result here. All the conditions of the theorem are fulfilled. Our chain is definitely irreducible. It's aperiodic, and it's positive recurrent. So let's just go ahead and evaluate these long-run probabilities. So pi transpose P equals pi transpose. Well, this would just imply that we have P1 times 0.6 plus P2 times 0.5 is equal to P1. Then we can write down the other equation as well, but that is a redundant equation, of course. Okay, so now we can just choose these two equations, solve for P1 and for P2, and I guess so this gives us a solution of P1 is equal to 5 over 9, and P2 is equal to 4 over 9. So now, and part B now. If we start the process with coin 1, what is the probability that coin 2 is used on the 5th flip? Yeah, well, part B is easy. So So if we start now, I'm assuming that this means the first flip and not the 0th flip. So if we start with coin 1, what is the probability of using coin 2 on the 5th flip? So what is the probability of going to state 2 in 4 moves? And that, I think, yeah, you can just do it on your calculator and find it. It would be the 1, 2 entry of this matrix multiplied 4 times with itself. And I guess Professor Witt has calculated it. It's 0.444. Any questions on this? So the question is why it's not, sorry?
Why is it not the sum of P12 and P22?
And well, okay, so the question is why is it not the sum of P12 and P22? Well, it's because we're assuming that we start the process with coin 1. So we start from state 1. Okay. Okay, so let's move on. Oh, didn't want to erase this. Anyway. So let's do now problem 20. So problem 20, we have transition probability matrix P is doubly stochastic. So P is doubly stochastic if, in addition to all its rows, which have to sum to 1, right? Because they are transition probabilities, and you have to go somewhere, so they have to sum to 1. But in addition to that, P is called doubly stochastic if all of the columns also sum to 1. So over all I, okay. So now if such a chain is irreducible and aperiodic and consists of m plus 1 states, so the chain is irreducible, aperiodic, and consists of m plus 1 states. So it's a finite Markov chain, which automatically makes it positive recurrent. Then prove that pi j is just equal to 1 over the number of states. So now we use, so this is just a very short proof. We use the previous theorem now. So we know that there exists a unique probability distribution. So there exists a unique non-negative pi such that pi p transpose p is equal to P transpose, and P transpose E is equal to 1. So we know that it's unique. And now we're asked to essentially verify that this choice of pi does the trick. So let's try. Pi transpose equals to 1 over m plus 1, 1 over m plus 1. And this we can, of course, just take the constant out of the vector and just say that this is 1 over n plus 1 times E transpose, where E is just the vector of all ones. So let's see if this works. Well, okay, so let's try condition 1. So for condition 1, let's see. Transpose P. Well, it would just be equal to 1 over m plus 1 times E transpose times the matrix P. Okay? Well, so the constant we're fine. We're fine with. Now, what is E transpose P? Well, it would just be the sum. So this would give us another vector, right? And each element of that vector would just be the sum of all the elements on a particular column of the matrix. And we know that those sum to 1. So we could rewrite this as sum P I1 I equals 0 to n plus 1 oops n I'm sorry this is just elementary operations with matrices and vectors. And now we know by definition, because the matrix is doubly stochastic, all of these guys are just equal to 1. So what do we get? We get 1 over m plus 1 times, again, the vector of all ones. And, well, this is definitely equal to pi transpose. So the first condition is satisfied. Now let's see if the second one is. And the second one, we just want to make sure that pi transpose E is equal to 1. Well, again, that's not very hard to do, because what do we have? 1 over m plus 1 times E transpose E. Well, what is E transpose E? It would just be 1 plus 1 plus 1 plus 1 times the number of states. So this would just be 1 over m plus 1 times m plus 1, which, of course, cancels out to 1. So the second condition is also met. So we have just verified that in the case of a doubly stochastic matrix that is irreducible, aperiodic, and has a finite number of states, then the only possibility, or in fact, of course it's the only possibility, but the stationary probability distribution is just the same for all states. The probability is the same for all states, and it's 1 over the number of states of the chain. Any questions? Okay, let's move on. Now let's do problem 30. I think Professor Witt told me that he did a lot about trucks and cars and things like that in lecture, and I wouldn't be surprised if something very similar is on the exam. So these are good problems to know how to model and to solve. So 3 out of every 4 trucks on the road are followed by a car, while only 1 out of every 5 cars is followed by a truck. And we want to know what long-run fraction of vehicles on the road are trucks. So let xn be equal to 0 if the nth vehicle is car, and let it be equal to 1 otherwise, or if it's a truck. Okay? we know that 3 out of every 4 trucks on the road are followed by a car, while only 1 out of every 5 cars is followed by a truck. Okay? So let's see. So if we observe a car, what is the probability that the next vehicle that we see is a truck? Well, it's going to be 1 over 5, because let's see, only 1 out of every 5 cars is followed by a truck. Followed means that, what do you see first? Only 1 out of every 5 cars followed by a truck. Well, yeah, so if you see maybe I'm not getting this. So 1 out of every 5 cars is followed by a truck. So if you see a truck, so if you see a car, then the next car that you will see will be, oh, okay, I see. Sorry. Yeah, so P00 is 4 over 5. And P11 is just 1 over 4. Yeah, I wasn't getting the grammar there. So this means P01 is equal to 1 over 5, and P10 is equal to 3 over 4. Okay? And now, what fraction of vehicles on the road are trucks? Well, we do the same thing. So transpose P is equal to pi transpose E is equal to 1, where now P is the matrix defined by these probabilities. And, you know, we get the following numbers. So that's that problem. And now I'm going to do any questions on this? No? Okay, so I'll do a couple more problems that I just think are good to look at. And you might have them on your next problem assignment, but I think we have some time, so. Okay, so let's do problem 34. So in problem 34, we have a flea moving around the vertices of a triangle in following manner. So we have a triangle, and we have a flea that if he's on vertex I, he will go clockwise with probability Pi and counterclockwise with probability Qi. So, you know, we'll go this P1, Q1, P2, Q2, P3, Q3. Okay. And so there are 2 questions. We want to find the proportion of time that the flea spends at each of the vertices. And then we want to calculate the probability of how often does the flea make a counterclockwise move, which is then followed by 5 clockwise moves. Okay. So first of all, let's just write down the probability transition matrix. Well, it's fairly easy to do. So from vertex 1, we go to 2 with probability P1, and we go to 3 with probability Q1. And similarly here, similarly for the other vertices. So this is P. And to calculate the long run probability of being at any vertex, we solve again the same equation. And I didn't actually do this, but you solve for this. I mean, it doesn't matter what values you get, essentially. So we solve. Now, the more interesting question is the second one. So what is the probability of making a counterclockwise move, which is then followed by 5 consecutive clockwise moves? Make counterclockwise move followed by 5 clockwise moves. So, does anyone have any ideas how you would go about calculating this? So Q1, yeah, but it's definitely the right thinking. But we want sort of kind of a limiting result, right? How often, in the grand scheme of things, does this pattern happen? So we would have to account for it in some way. We'd have to somehow use the long run probabilities, right? So we condition, you can say condition on the vertex on which we're on. So if we say that this is event A, so probability A is equal to probability A given we're at vertex 1 times the long run of probability of being at vertex 1, so times pi 1, plus probability A given being at vertex 2 times P2 plus probability A given 3 times pi 3. And now, what is probability of A given 1? Well, now like we do what you suggested earlier. Because now, if you're at vertex 1, then, well, in the beginning you have to go counterclockwise. So that happens with probability Q1. And then you have to make 5 clockwise moves. So then you start from vertex 3 now, and you start going clockwise. So P3, P1, P2, P3, P1. And so on and so forth for the others. So probability of A given 2, that is just Q2 times P1 times P2, P3, P1, P2, and then probability A given 3 is Q3 times P2 times P3, P1, P2, P3. And then we multiply these by the respective long-run probabilities, and we add them up, and that is the probability of that event. And in general, whenever you're asked to calculate something, that happens how often or what proportion of time or, in the long run, what happens, you always somehow have to incorporate these stationary probabilities. Because they give you the long run proportion of time that you're in states A, B, C, or whatever. So now, last problem I'm going to do for today is problem 36. Okay. So now we have a Markov chain, and the state of a process changes daily according to a Markov chain. So let's say, xn is the state at day n, and xn can take one of two values, 0 or 1. And we have the following matrix, 0.4, 0.6. Okay. And so our system evolves in this way. And every day, something else happens too. A message is sent. And if the state of the Markov chain that day is I, so every day we send a message. So if xn is equal to 0, then the message is good with probability p0. And if xn is equal to 1, then it's good with probability p1 and bad with probability q1. Okay. So, does it make sense? Okay. Okay. So now we're asked a few questions. So if the process is in state 0 on Monday, what is the probability that a good message is sent on Tuesday? So what is the probability of a good message Tuesday, given, let's say, on n plus 1, or on day 1, or day 2, given that x1 given that today we're in state 0. So, well, the way to solve this problem is to, of course, again, condition on what happens on Tuesday. So in what state will we be in on Tuesday? Because that is information that we need to have in order to determine whether or not, or with what probability, our message will be good or bad. So we condition on x2. So let's call this event A again. So this is equal to probability A given x2 is equal to 0. This one is 0 times probability x2 is 0. Okay. And so given that we're in state 0, we know that the message is good with probability p0. So it's p0, and of course the probability of going from 0 to 0 is p0, 0. And similarly, the other factor is just p1 times p0, 1. And these are all numbers that we have, quantities that we know. So we can calculate this. Now let's do part B. So if the process is in state 0 on Monday, what is the probability that a good message is sent on Friday? So what is the probability of good message on day Friday 5, given x1 is equal to 0? Well, I guess it's pretty easy to see that it's very similar to what we have here. The only difference would be now that we need to consider the 4-step probability transition matrix. So it would be exactly the same as before. So it would be p0. But now we need to know the probability of going from 0 to 0 in 4 steps as opposed to 1. Okay. Now let's do problem part C. In the long run, what proportion of messages are good? So any suggestions? Well, I would say that very similarly to the previous two problems, it would just be p0, but this time times long run probability of being in state 0 plus p1 times pi1, where the pi's can be calculated in the usual way. Okay. So now let's do part D. So let yn equal 1 if a good message is sent on day n. 1 and 2. Okay. And so the question is yn a Markov chain? This is an interesting question. So is yn a Markov chain? So what do you think? It's not an easy question to answer. It would seem like it is, because the past really has no relevance. Like, to predict the future, you basically only need to know the present. But there is that issue again of whether or not these probabilities would change over time. And that, I think, but anyway, let's try and see. So say that we wanted to calculate this probability. Okay. So let's see. So let's calculate the probability that message is good. Actually, is good on day n plus 1, given that it's good on day, or given that it doesn't matter, yeah, given that it's good on day n. Ideally, we would like to find something that is independent of n. We've already argued that that the first aspect of the Markov property holds, because past information really has no significance. So now we want to see, is this probability independent of n? Okay. So, of course, to calculate this probability, we really do need to know what the state is at time n plus 1. That's vital information to know, because it changes the kind of probabilities that we'll be considering. And to know what the state is at time n plus 1, well, we'd also want to know what the state is at time n. So let's condition on xn. So okay. Actually, okay. So what is this probability? This probability we actually can calculate. So given that we're in state 0, we want to know what is the probability of having a good message being sent on the following day. So, this would just very simply be it'd be P0 times P00 plus P1 times P01 times this probability here. And we do a similar thing for the other expression. So this is P0 times P01 Okay, so now we need to look at these two probabilities. And let's just focus on one of them. Let's focus on this one. So let's see. So what is probability of xn equals 0 given yn is equal to 0? Well, we can use Bayes' rule here, try and figure this out, but that won't really help that much. So just by using Bayes' rule, okay. So now this we know is just P0. And we're left with the following thing. Okay. So, and this is as much as we can do, really. I mean, we can keep conditioning in the past, on the past, but eventually this is the best that we can do. And I say that this shows that Yn is not a Markov chain. And the argument is it's not very rigorous, but I think it's pretty intuitive. So this probability is definitely not independent of n. Isn't that right? Like, for example, if you have some kind of Markov chain where with very high probability you keep going back to a certain state, then say that you have a Markov chain where probability xn is equal to 0 converges to a certain number. It can happen. It can definitely happen when you're multiplying that matrix. It can be that it converges to its long-run probability. Well, then this probability is definitely not independent of n. It will depend on n. So we cannot say that the transition probability is the same for all n. So we say dependent on n. So hence not a Markov chain. And sort of the final note would be, well, how would we sort of make this into a Markov chain? And so to make it into a Markov chain, we can consider so in other words, we can consider the process as a vector. So where in each stage we keep track of both the state that the process is in and what the quality of the message is. So, I mean, in this case, you can, and this would be a Markov chain. Any questions? Well, if there are no other questions, thank you.